I'll do a short introduction before you start, Lin. So Lin Liu received his bachelor's degree in geophysics from Wuhan University in 2005 and his PhD in geophysics from University of Colorado at Boulder in 2011. Then he became a George Thompson postdoctoral fellow at Stanford University. And from 2014, he went to the Chinese University of Hong Kong and worked there as an assistant professor and then an associate professor. Lin's research interest involves mostly cryosphere geophysics and space geodesy, and he received the 2021 John Ward Early Career Award from the AGU in recognition of his contribution to space geodesy. Today, he'll talk about geophysical investigations of the thawing permafrost. Time's yours.
Thank you, Eric, for your nice, kind invitation and introduction. It's my great pleasure to talk to you about my research in this particular topic on geophysical investigation of thawing permafrost. I chose this particular photo as my title picture, was taken a few years ago in northern Alaska. This is actually nicely summarized what I wish to convey in this talk. This is what happens once permafrost is thawing. And you can see here it's actually literally this particular condition, permafrost stores a large amount of ground ice that melts and literally the surface collapses. And that results in strong surface deformation. And in the meantime, so the ecosystem, the vegetation, the surface hydrology are being disturbed. The carbon that was originally frozen in permafrost now become exposed and mobilized and decay. And that turns out to be a big issue because it releases carbon dioxide and methane into the atmosphere as thawing out. And as this strong thawing condition occurs under this setting, the heat, the water and the gas exchange between the ground and the air become very strong now. And so that interactions become very complicated and enhanced. And last but not least, if you see here, the background is the Trans-Alaska oil pipeline. So if you can imagine if such strong disturbance extended beyond and near the infrastructure that can threaten the stability of the structure. So throughout this talk, I hope to convey you a few messages. Oops. All right, so first of all, thawing permafrost has actually very big impacts. Summarized briefly over here, we're talking more about that. But turns out it's actually not easy to study, mainly because permafrost, by definition, is underground thermal phenomena. Most of the geophysics tools cannot detect the ground temperature, for instance. And in particular, I'll focus on my topic regarding the abrupt thawing as shown here. The thawing can be very abrupt in this case, and it's very dangerous, yet very poorly understood. But on the positive side is that geophysics in general offers essential tools and could quantify and monitor thawing permafrost. All right, a brief introduction about my group. As Eric mentioned, I manage a relative model-sized group with now 6 students. We use geophysics, geodesy, remote sensing, artificial intelligence, aiming to observe, characterize, understand cryosphere processes. Even though I'm based in Hong Kong, I'm being lucky to receive research funds funded by the Hong Kong Research Grant Council, similar like NSF of Hong Kong, and we're looking at different cryosphere problems such as Greenland ice mass loss, and thawing permafrost in Arctic and Tibet. This is the talk I will focus on today. And another topic is regarding rock glacier kinematics. By the way, if you recognize, this is Enzo now actually doing a postdoc in UTIG, working with Ginny. All right, so just make sure on the same page, if you're not very familiar with permafrost, I will tell you that, spend a few slides and tell you some basics about permafrost. And starting from the definition, actually permafrost is not equal to permanently frozen grounds. Actually, permafrost is no longer frozen to a certain extent. And permafrost turns out covers a very large area and stores lots of carbon and permafrost thawing. Then I will use two case studies to illustrate, to showcase how geophysical methods can be used to investigate permafrost degradation. In the first one, it's a combination of various methods, including ground penetrating radar, and the other two are kind of a remote sensing method. To a certain degree, they're all geophysical tools as well. That's we use to combine them to study thawing permafrost after human disturbance. The second one, I'll talk about a relatively new technique called surface NMR for imaging the subsurface permafrost thaw. Okay. I chose those two. I'm trying to orient it to UTIG audience because most of you are geophysicists instead of remote sensor. I forgot to mention that back in summer 2019, I visited Anne. I gave a talk about the remote, focus on remote sensing on permafrost. So today I chose to focus on more about the geophysics side. Then towards the end, I hope to offer a few of my thoughts about future developments. By the way, please feel free to stop me if you have any questions. All right. So permafrost by definition refers to ground that is temperature whose temperature remain at or below 0 degrees C for at least two consecutive years. So the definition is purely based on the temperature. So here's the permafrost, and it's more for geophysicists easier for us to get the temperature curve on the right. So this is the temperature profile versus depth. Okay, and 0 is here. Okay. And within permafrost, even though there's actually annual change, the summer the temperature is higher, the winter temperature is lower, but throughout the year it always remains to be below 0. So that's the permafrost. Above permafrost is a layer we call active layer, corresponding to this photo showing here, which thaws in the summer because temperature rises above 0 and freezes in the winter. Okay. And so that already points down that fundamentally there are two quantities that are relevant and super important for permafrost. One is the ground temperature. What's the temperature of the ground? The other is the thickness of the active layer, because that determines a lot of hydrological, ecological vegetation processes at the surface. So these two are also the main concern of the field measurements. And there are global networks measuring ground temperature, measuring active layer thickness. And together, these two quantities are regarded as the essential climate variables under the UN framework. So it's a very big deal in permafrost studies. So that's already, if you want to look at ground temperature, geophysics is not the best way to do that. However, geophysics can be used to detect or to measure active layer thickness. I will get into that in the second half of my talk. So where's permafrost? It turns out is the largest cryosphere system by area. So what you see here, the brownish color showing you the permafrost zones on land. So taken together, they underlay about 1/4 of exposed land in northern hemisphere. So 80% of Alaska, half of Canada, most of Siberia. So even for Tibetan Plateau, about 80% of the surface are actually underlain by permafrost. And permafrost also developed at subsea. You have colleagues from UTIG looking at subsea permafrost, and that's the dark green color showing here. They developed in the last ice age when the ice shelf, continental ice shelf, was actually exposed. Continental shelf actually was exposed to air and now submerged beneath the rising sea level. So even under this, the OC today in the Arctic, subsea permafrost extend about 2 million square kilometers. But they're suffering, they're shrinking, the area is shrinking as Arctic has been warming up. All right. Oops, that showed up earlier than expected. Please ignore this for now. But permafrost also turns out to store some organisms, including mammoths, and this is very iconic ice baby frozen mammoth in permafrost in Siberia, and there's also, if you can see this second picture over here, large, thick, dark sediments, the carbon-rich frozen sediments dating back late Pleistocene. They're called Yadoma. They contain large amounts of carbon, mostly in frozen roots, vegetation roots. And taken together, this is to compare the different carbon pool, carbon reservoir in the Earth system. Well, the large, of course, is the deep and intermediate ocean. This is in the scale is in gigaton. And the permafrost here is, and more until the recent decades, we now realize that permafrost actually stores about more than 1,600 gigatons. So that's more than about twice as the carbon as stored in the atmosphere. So there's actually a concern. Oops, okay, that's why. There's a concern is as the Arctic's warming up, okay, so permafrost thaws and degrades. Well, the consequence of that is the active layer becomes thicker and this part of permafrost thaws. And then those carbon that was originally frozen and becomes unfrozen and undergoes decay, carbon decay, because the microbes and bacteria become very active. And this process would emit CO2 and methane into the atmosphere and making the viscous cycle, because there's more greenhouse gases in the atmosphere that make it this positive feedback. There used to be a very big concern a few years ago, could be a carbon time bomb that can explode and release a lot of carbon into the atmosphere. More recent years, there's more efforts or convergence between the modelers regarding the contribution of permafrost carbon. All right, so as I mentioned, permafrost has been thawing globally. This is looking at the northern hemisphere. I'm just using my change that to laser pointer, maybe it's easier. Okay, so these are each circle actually represents the field-based sites with borehole measurements, measuring the ground temperature. So this is summarized in the most recent paper, just published a few weeks ago, summarizing the warming trend observed from those boreholes in mostly around the Arctic, but there's some sites over Tibetan Plateau. And the larger the circle, it means the larger the warming rate. So if we look at northern Alaska, for instance, coastal Alaska, the warming rate in the past decades is about 0.6 degrees. And that the rate decreases as we move to interior Alaska. And for instance, northern Canada and Greenland is alert, okay, in northern Canadian Arctic, and the warming rate is reaching to about 1 degree per decade. So that's really a big deal. Even in the lower latitudes, such as Tibetan Plateau, it's also observed a warming trend. So there's no argument, there's no doubts that permafrost, just from observation perspective, permafrost has been warming right from the temperature records. This is showing you from the same review paper summarizing the active layer thickness. The mentioned is thawing and the top layer that becomes thicker and thicker, and that's being observed around the globe. Okay, and this is in centimeter level in the past 30 years or so. So no matter whether you can look at Siberia or interior Alaska or Greenland, has been always rising. The only outlier, which is interesting, is the north slope of Alaska. Even though the temperatures have been rising, but active layer remain relatively stable. This is the reason behind that is underneath the active layer is ice, is a layer that is almost reaching ice. So when ice melts, that does not contribute to the thickening of the active layer. At least that's what I think, and there's an early study of me to demonstrate from geophysical perspective that what's behind this non-increasing trend in northern slope, on the north slope of Alaska. All right, so here's north slope of Alaska, and zoom into the coastal area around Puto Bay. And there are literally tens of thousands of lakes like those. Those are known as Thermokarst lakes. They actually form because of abrupt thawing of permafrost, and they're everywhere. So how they form? Okay. So initially, there's certain local places where we have ice wedges, just pure ice developed underneath the ground. And upon warming, those ice melts, and then the ground locally subsided and fill water and to initiate small water bodies like ponds. And as this becomes lower elevation, the water nearby would tend to flow towards and the ponds would those ponds merge into bigger lakes. And once the lake water reached to more than 2 meters, it would remain unfrozen even in the middle of winter. So that the unfrozen water would continue to thaw to warm the soils below, and that forming what we call thaw bulb or talic, and then the permafrost. And that's also, maybe if some of you saw videos or amazing pictures showing you actually frozen bubbles, methane bubbles that rising out from the thawing permafrost. Recall that permafrost stores a lot of carbon, and once it thaws, and methane would develop and rises up and become frozen in the frozen lake. And so this process would further enhance this feedback processes and accelerate carbon dioxide releasing. So later on, so here's a good time to introduce this terminology. Talic simply referring to this thawing bulb, this thawing condition, and this lake body. And I will come back to it and show you how we can image such thawing permafrost beneath the lake body. All right, and so here's a summary about abrupt thaw. Okay, and in addition to the thaw lakes, the Thermokarst lakes, there are various processes or disturbance that can lead to abrupt thaw, such as fire, such as landslides, lake drainage, and so on and so forth. So abrupt thaw is much deeper and faster than the gradual top-down thawing, and so it could be thawing could be happening over 1 meter within a year, but given such complexities and such strong changes, unfortunately, they are not very well understood, and such complexities not including any large-scale permafrost models, and that leaving a very big knowledge gap about permafrost, the change in the future, and what are the impacts. So as a geophysicist, I'm turning from not a modeler, so I mostly doing observational studies. My overarching aim for my research is to quantify the location, where they are, where are those disturbance abrupt thawing are, when they occur, what are the magnitudes, what are the rates, and what are in their impacts. So the two main kind of tools I'm using, including remote sensing, that mainly for measuring the disturbance that we can see from the surface, okay, and the near surface geophysics for detecting the underground thaw and the associated structures and processes. This is a summary I borrowed from this paper, and summarizing the remote sensing application for study permafrost. There just simply a very wide range of remote sensors from in space mostly can be able to use to address various problems. Okay, I mentioned active layer thickness. The thermal sensors can measure land surface temperature and ground temperature. Of course, you can look at surface water. You can look at the wildfires and even detect greenhouse emissions. Okay, and so remote sensing, as you can imagine, they're limited to the surface feature. Okay, but they're good at measuring those features at regional scales and at the operational and long-term basis. And on the other hand, near surface geophysics, there are also wide range. Many of you are familiar with different geophysical methods. I borrow this summary diagram from this paper, and they're looking at different geophysical, near surface geophysical methods, how they can be used for study permafrost. This diagram should compare, just illustrate their spatial coverage of various geophysical methods such as ground penetrating radar, electric resistivity tomography, and seismic refraction MMR, and time domain EM. This is looking at their spatial resolution. So some of them, they are suitable for plot-based, while others are looking at the intermediate scales with spatial average about 10 to the power of 6 square meters, while some of the airborne sensors are offering regional scale coverage. This one summarize the depth of investigation, because that's what near surface geophysics is particularly good at. It's not just stretching the surface, but looking penetrating deeper, as some penetrate about 10 meter deep, some can see through hundreds of meters. So depends on their depth of investigation and vertical resolution. And so geophysical method can be used to study active layer, in particular active layer thickness, can be used to look at the atolic and lithology of permafrost and even the thickness of permafrost. So already you can see that near surface geophysics actually can be serve as important medium to bridge the large gap between, in terms of permafrost characterization, between size scale observations, which are on this order, and remote sensing scale, which is on this order. And so that's why I see a big advantage of combining near surface geophysics and remote sensing. So a few examples, it's not my study, but I just want to highlight a few very groundbreaking and interesting ones using near surface geophysics. This particular one is led by USGS Bert Linsky. So they actually flew a helicopter over the interior of Alaska and near Fort Yukon. And this is an airborne EM instrument which send out primary EM fields that interact with the subsurface, in this case permafrost, and that generate secondary EM fields that being picked up by the receiver, okay, also carried by the helicopter. And this is the results. The color actually indicates showing here is showing you the electric resistivity. Okay, from permafrost, if it's frozen, it's actually very resistive. Okay, it's not a conductor. It's a poor conductor. It's on this side. But once it's thawed, it becomes very conductive. So it's on this side. So from this very this is in kilometer scale. This is airborne, and this is vertical scale. How it can, this is surface, it can penetrate into hundreds of meters, about 100 meters into the ground. So it's offering us unprecedented detail regarding the subsurface structure. Okay, the surface remain frozen as permafrost. Okay, and beneath that you can see this light color or blue color indicating the thawed condition of the permafrost. In this particular case, showing up here, there's a lake. It's called 12-mile lake. This is a very big lake, relatively speaking. And so, as I explained earlier, if this lake is big enough, it's thick enough, it's gonna form a thaw bulb. So that's what's this part. The lake talic is unfrozen ground. All right, and next to it are the frozen condition. So this actually imaging that is actually the thaw continues. It's not just limited and this the lake. It's actually connects to very thick, hundreds of meters, and that connect to the groundwater system. Another study is actually done by Maniani's group. Is looking, they're also using the near surface geophysical method, in this case ERT, electrical resistivity tomography, and looking at they conduct ERT survey extended from the terrestrial, from land over a lagoon underwater. So the color still look at the resistivity. Again, if you see high resistivity, meaning frozen ice or ground or permafrost. So based on their study, which was published 2 years ago in Science Advance, they actually demonstrate really well, and that's actually the frozen condition is the icebound permafrost, only limited to the onshore part. All right, and beyond over the lagoon part and then over the ocean, the sea area, there's not much frozen ground anymore, as shown here, because that's what the very low resistivity shows. And because that's before their work, most of the permafrost, this is the conceptual, widely accepted conceptual model, thought the icebound permafrost would continue extend from land and continue over the continental shelf and like this. But according to the ERT survey, the ERT results showing there's not much frozen. But that also meaning there's actually active transport of groundwater or other heats and other mass condition transport and exchange between the onshore part and the offshore part of the system. Now back to the work I was involved in, I led in a few years ago in optic, and in this the first case study looking at the permafrost thaw after human disturbance, and this look at northern Alaska again, and this highway leading from called Delta Highway leading from Fairbanks to the to Protocol Bay near the coast, and this showing you the Alaska pipeline. Okay, so there's actually a road that was built simply to access to the Alaska pipeline, and you can already see the maybe you can tell. I will show you on the next slide some the development of such feature. There's some disturbance over the ground. This is showing you the over zooming this region, and the color actually showing the elevation. This is based on LiDAR. And there's some micro topography showing actually essentially high and lows. There's expressed as hummocks and depressions. And in this place, the permafrost contains very high content, ice content up to almost 100%. I'll show you in the photo next slide. And we did some field surveys, we visit there, and we probe into the active layer. We also conduct a GPR, ground penetrating radar, along a relatively short transect. This is actually a relatively small area. So from here to here is only about 200 meters. So our survey line was about 200 meters. Roughly give you an idea how it's developed. So look at historical air photos in the 1950s and 1970s. Everything seems to be okay. It's typical Arctic condition, relatively stable, even though there are thaw lakes everywhere. And once the roads and the oil pipeline being built, okay, and you can see here this lake drains, but actually this road blocked the drainage of the lake, and nearby there's actually water being accumulated there. So there's a human disturbance, and turns out that blocked the drainage of the hydrological systems there. And yet in the first few years after the infrastructure building, there's not much going on in terms of permafrost, and at least the surface seems to be still relatively stable. But that's not 10 years later, you start to look at this disturbance, and in the more recent years, and can see there's actually expansion of the disturbance, indicating the Thermokarst formation and expansion. All right, so we did a GPR survey. This is the site condition when you go there. There's not much undulation on the surface, but it's only but it can be well resolved from the LiDAR DM. And you can see here we actually dig a hole. You see here is almost pure ice, okay, after just a few 50 centimeters. So I ran a GPR, and turns out it's actually a very easy task for GPR. GPR is essentially to send radar pulses, the transmitters and the radar pulses that propagating through this medium, which in this case a thawed active layer that is, and then reflected at the interface between the active layer and permafrost. So such interface is actually showing you a very strong contrasting dielectric constant, this epsilon R term there, which is also known as relative permittivity. So once the thawed active layer contains high soil moisture content, so it's close to 20. But permafrost frozen is like close to dry soil and dry rock, so that has a relative low permeability, and turns out this is actually a very strong reflector for GPR. So by measuring the two-way travel time, if you know the velocity, we can estimate the thickness of this active layer. All right, so this is the radargram. It's a direct outputs from GPR. So the vertical axis now is the two-way travel time in nanoseconds. And the green line actually indicate this strong reflector that's between the active layer and permafrost, as I alluded earlier. So this is actually our regular case, and we're happy that, and then with that, we run this routinely in our field work. But at this particular location, and just extended right next to this regular case, we start to see two reflectors from the same radargram. So once here is continue from the from extending from that same interface, but there's a deeper one. So we were curious, and we dug a pit and to look at what's going on, why there are two interfaces. And you just I don't know whether you can see here the structure from the soil grain size and condition. You can see here actually there is some contrast at the surface. It's a peat, organic, highly organic, up to 90% organic soil. And beneath that is the silt, fine grain. Okay? And so that interface really corresponds well with these two layers we saw. So what the message here is, in addition to detect the boundary between active layer and permafrost, we also start to see soil stratigraphy within the active layer. But just outside these zones, everything starts to be normal. And so here showing you a longer profile. Well, and now I show you instead of two-way travel time, I convert the travel time with the active layer thickness, and that is done by calibrating the GPR survey with the probing, which is the get the absolute thickness or depth of the interface, as showing as the circles. All right, so the solid line is from GPR, the circles are from the probing, and so the the black line indicate the interface between active layer and permafrost, and where you see this red line, actually it's just showing where we found the two-layer structures. On top is the peat, beneath is the silt. Then we overlay this on the topography on this, and found an amazingly consistency between the occurrence of the two-layer feature with the surface microtopography. Wherever we saw there's a depression, we saw such two-layer structure, where over the hummocks places, there's only one structure, simple peat layer. So this is our conceptual model to explain what is going on. This is a stable condition. It's before permafrost degrades. It's typically organic rich peat layer on top, and then organic poor or mineral rich soil at the bottom, and this frozen. Okay, the permafrost table is here. Underneath that, the frozen silt is the ice rich permafrost. But this after the road was built and this undergoes strong disturbance, and then at local scale. Okay, and this local place, the strong depression, Thermokarst processes occurring, deep thawing occurs that disturb causing the surface depression and also disturb the soil of the active layer. So now here dashed line is the new permafrost table. So whenever we do, so that's over here, the depression actually where explain why we found two layers, the peat and the unfrozen layer. Over here, now, what causing the formation of hummocks? Actually, over here is the migration of water from the deeper part from the thawed portion over here, and water migrates to this local colder areas and form an ice layer, and that's results into hummocks. So that's explain why, from a GPR perspective, we only see a very beautiful, only single layer peat. All right, so that's not the end of story. As I mentioned, we also apply remote sensing to characterize Thermokarst. In this case, in the same site, we apply INSAR. Many of you know this, how INSAR works as a satellite. In this case, a satellite space-borne INSAR measurements used by using the phase information taken from the SAR images taken from path 1 and path 2. We're able to precisely measure the surface deformation. So we're able to measure up to 10 times of surface deformation. In this particular study, we use the Japanese ALOS-1 satellites, and we are mainly concerned with the surface subsidence trends. And over this 5-year period, the spatial resolution is about 60 meters. The accuracy is on the order of 1 centimeter per year. We also managed to get hold of airborne LiDAR data. This is a campaign survey which can generate very high resolution digital elevation models. In this particular study, the one we used is at 1 meter spatial resolution. The vertical accuracy is about 10 meters. So we are able to use it to estimate the net subsidence. I'm going to only show you the results. All right, here showing you the INSAR results. I hope you recall where the boundary of the Thermokarst landform there. This is showing you the color actually indicate the subsidence trend over that 5 years in centimeter per year. That amazingly match well with the boundary of the surface depression, which is not a big surprise though. Also equally important, in terms of rates, is up to 8 centimeters per year subsidence. Equally important, we're able to quantify the error or the uncertainties in the trend, which is on the order of 1 to 2 centimeters in this case. So immediately, this particular remote sensing method can already tell us roughly where the location of the abrupt thaw, okay, and what's the trend and the associated uncertainties of the subsidence as a result of the thaw. All right, this is the LiDAR, DM, a very fine spatial resolution, the 1 meter, and the 10 centimeter vertical accuracy. So the underlying assumption is we assume, so this is the same conceptual model again, since we only be able to get one, there's no time dependency or time series DM data we were able to obtain. So even from this one single shot, okay, just looking at the one, this micro topography, we assume everywhere at the top of the hummock represent original condition, which was here. And now the depression, the elevation drop between the hummocks and depression just tell us the net subsidence across the development phase of this landform. And as we do a gridding and just indicating the net elevation change up to 1 meter throughout the whole process. The last step is to relate everything together, relate this net subsidence with the inside subsidence trend. So on the horizontal axis, the inside subsidence trend. On the vertical axis is this elevation drop from LiDAR. So the rates, the ratio between the two actually gives us time, even though it's quite scattered. But to the first order, we still decided to fit a linear trend, because that at least tell us the time scale. The slope tells us the time scale, meaning that give us a characteristic time of this development, which is about 8 years. So quickly move on to the second study, focusing on the TALIC, the thawed bulb, the thawing bulb beneath the water body, and how we use geophysics method to take an image of that. So this is the use of, this is led by Andy Patsikian. Just remind you, I've shown you this ago, and we're looking at this thawed permafrost beneath the lake, because both the size and depth of the thawed permafrost, in this case TALIC, are related to the greenhouse gas emissions. Okay, so that's an important characteristic we want to estimate before we can say something about the carbon story. And of course, you can imagine it's not easy task. How do we know what is the size and depth of the thawed condition? It's going to be expensive and difficult to drill into the lake beds. All right. So we decided to give NMR a try, nuclear magnetic resonance. Okay, and in this case, it's a near surface setting. Okay, Mark told me that he actually used ages ago. He used NMR in the laboratory setting, which is still used today. But in this particular case, we use surface NMR. So we laid out a coil on the surface. Okay, before we generate electronic magnetic field from this coil. Actually, in this case, it's a water body. Okay, and the protons, they're spinning, their orientation align well with the Earth's magnetic field from microscopic view. And once we generate artificial electric magnetic fields and then perturb the spin of the protons, and then we shut the transmitting EM field off, and the perturbed protons, they're gonna relax, they return back to their original condition with original spin orientation. In this process, NMR theory tells us that there are going to be secondary EM field generated by this relaxation. So by measuring such relaxation, we're able to directly estimate the water content. So that's drastically the difference, the main difference between, or the advantage between NMR and the other geophysical methods is that it actually is able to directly measure water contents. Since it's directly sensitive to water, liquid water, and it's not sensitive to solid matrix. And so, once we're talking about permafrost. If it's thawed, that means it contains liquid water. But if it's not thawed, it's permafrost or ice. It's NMR is not sensitive. That making it very suitable to address our problem. And it's a non-invasive measurements of water content as deep as 100 meters. So, so we just simply, the idea simply laid out a coil on the surface, and in the middle of winter, when the lake was frozen. And this similar idea is like taking the MRI of this thawed permafrost. All right, this is some field photos. This we did in March when the lake was solid frozen. This was me with other colleagues. I was dragging deploying the coil on the surface. And okay, all right. So we did this surface NMR study at the 3 lakes outside Fairbanks. All right, they have different sizes. Okay, this is the same scale, 100-meter scale. The 8th lake over here, 8th lake is the largest, and you see that we laid out figure 8 coil. Okay. And Caribou Lake, so there are 2 lakes. The other side is close to a borehole. It's not a lake. Okay, so the results. Okay, showing you the vertical. This is directly from. This is the results from NMR. NMR tell us water content directly, okay? And it's showing us the vertical profile of the water content. So near the surface, because the lake was frozen, so it's pure ice. So the lake, the liquid water content, this would be liquid water content is 0. Okay, I moved to here because this is a bigger lake, and this is about 4 meters thick water. Water was not frozen. The lake was not frozen, so that's 100% water content. So what's very interestingly is this: right beneath water body is the lake sediments, which show us something about 30% water content. It's simply showing that, indicating that it's telling us that this is unfrozen. And even beneath 8 meters or even deeper, this shows us the maximum penetration depth, which is about 22 centimeters, 22 meters in this case, still remaining about 20%. That's just showing us that beneath this particular lake is thawed here with very good confidence, and even could be thawed over here. We extended the thawing to 20-meter depth. In contrast, over this smaller Caribou Lake, I still have this frozen ice problem with very relatively thin liquid water, unfrozen layer. Right beneath that, we still have this thaw bulb, but that's only extended about 4 meters in depth. Right beneath that, it's pretty much always frozen. Okay, and just to demonstrate over this particular place, and which is a dry, there's no lake, it's a dry condition. There's a borehole nearby which measures ground temperature, and which confirmed that from here to here, everything was frozen, and that's also what GPR shows. Also, interestingly, there is some potentially a thaw layer around 40 meters. So how do we interpret this? So for this one, the 8th lake is older, it's larger, and so there actually is an open thallic form that's connect directly from the lake sediments to the groundwater system. So everything beneath the lake is actually locally thawed. Whereas over this Caribou Lake, it's younger, it's smaller, and the thaw bulb still developed right beneath it, but it's pretty much limited right beneath, and there's no connection between this closed thallic with the regional groundwater. So that's how powerful this particular near-surface geophysical methods, namely NMR, surface NMR, can tell us. Okay, all right. So to quickly sum up, even though permafrost is difficult to study because it's purely defined by thermal states, covers large areas, remote, and it's very cold, involves very complex geological, biogeochemical, hydrological processes. But remote sensing and geophysical methods, and listed here, I'm not going to name them, offer essential tools to characterize, to study, and to detect where the thawing are happening and what are the impacts. There's actually new sensors and methods being developed and being implemented. One of the new ones that I'm particularly interested in, but I haven't put my hands on, are the distributed acoustic sensors. I suppose some of our ITIX colleagues are also experimenting with such new methods and data. And there are also new platforms, ground-based helicopter, aircrafts, and of course satellites, taken together. And it's of course it's much ideal if we can take in a synergistic approach to use multi-scale, multi-sensor geophysics, because that together, especially if you can integrate field measurements in geophysics and remote sensing and permafrost models to address such complex problems. Myself alone, even though I'm spending most of my time trying to look at how to bridge geophysics and remote sensing, but also working with field scientists and modelers, trying to make the connections with them. We're not there yet, but I'm working actively in such direction. All right, so again, a quick summary. Permafrost is fundamentally defined by subsurface temperature and thawing, and has big impacts. And the abrupt thawing is very it requires particular attention, but still relatively poor understood. So we all need those observations, direct observation, near surface geophysics, remote sensing are mutually complementary. They are all needed. And permafrost thawing will continue, and would continue and would accelerate according to the latest IPCC report. And that also calling long-term and global scale monitoring and modeling. So in that regard, geophysics definitely will play a more active and important role in both scientific investigation and in engineer. And I'll end with also kind of a very challenging problem, even though I'm a big fan of geophysics and remote sensing, but it's actually still we're puzzled, or we haven't figured out a way to directly estimate the ground ice content. I just leave that as a question mark, and hopefully some of you in the audience may help us or may have some clue to offer. So with that, I would like to thank you very much, and I'm happy to take questions if you have any. Thank you.
Thanks, Lin. Really nice talk. For all the audience, if you have any questions, please raise your hand. John, could you unmute yourself and ask a question?
Sure. Thanks a lot. That was a really fascinating talk. It seems like the ice wedges are really key to kind of initiating this whole process. But how do the ice wedges form?
Yeah. All right. I can maybe I can draw. Let me go back to. It's formed by cracking in winter. So it start to be like when the ground is frozen, it could crack. The crack form, tiny crack form in the middle in the winter. That is later, if it's remain there in the summer, then that's filled with water, and that crack gradually go opening up and growing into a wedge shape. And this process takes hundreds and thousands of years locally.
All right, thank you.
Next question, Anne. You need to unmute yourself, I think.
Sorry about that. Great talk, Lin. Great. It was very nice to catch up with you. So my question is, I know that you recently also have extensive work to study permafrost in Tibet. Could you give a quick summary on where the major difference in terms of the geological setting and where the main questions are there at Tibet?
Right. Thank you, Anne, for your question. The permafrost is actually quite different in Tibet and the Arctic. All right, because mainly because the climate and the geological conditions are different. In terms here, the active layer, this is a typical Arctic setting. So this is about 50 centimeter-ish, 50 to 1 meter-ish, and it's organic rich. And in Tibet, the active layer can be 2 meters thick, and is relatively dry, and it contains less organic matter. And permafrost in Arctic, in coastal Alaska, can be 500 meters thick, but in permafrost in Tibet, it's about 10 to 20 meters thick, and it's closer to 0 degrees. And in terms of the other geological settings, of course, Tibet is tectonically active, and hydrologically is complex, involves glaciers and snow cover and all that. So it has a different range of problems compared with Arctic. So in particular, my research, because relatively speaking, compared to permafrost in Arctic, permafrost in Tibet in terms of abrupt thaw are still relatively even worse, even poorly understood, and we know very little. So before we even know, we will want to address the impacts. Our first order question is where they are. Where are the disturbances are? Where are the abrupt thawing happens? So one of the recent studies, since you bring it up, just one last actual slides to show you is to map where are to identify where are the Thermokarst or where the abrupt thawing are. So it's showing actually the landslides in permafrost area developing that those outlined in red. So we end up just using optical images. We were able to identify about more than 800 thaw slumps along the highway. There's this yellow line, orange line indicate there's a highway and the railway. Those are super important critical infrastructures. And many of the landslides actually are nearby the highway. So that's one of our recent focus. But we haven't tried geophysics there because we first need to know where they are and how big they are. That's still in the work in progress.
Very interesting problem. Thank you.
Thank you.
Next is Kehua.
Hello, Lin. Thanks for the interesting talk. I have a question about so how you calculate the ground surface depression. So you use the Homaki elevation as a reference. But have you considered that actually the Homaki elevation can also change because you said there is more ice formed there, right?
Right.
And
Yes.
how will that influence your results?
Right. Yeah. Thank you for your question. I have to admit that yes, this is it was a quick and dirty way to estimate the net change of the Thermokarst landform, because you point out, and this one is there's ice core in it. That's why it's rising up, and it's unstable either. Because for this particular case, we only have one digital elevation model. This is the only data we had back then. So we just assume everything, as you point out, we assume everything using this as a reference is what's stable, and everything else that's going down is the net subsidence. But things has been changed. In Arctic, we have this very nice data set called Arctic DEM. They have extensive coverage over mostly entire Arctic, including permafrost area. They also offer you time series of elevation of different digital elevation models. I know some colleagues in the US, in the States, actually using that time series elevation, digital elevation model to track the evolution of their very large subsidence. Okay. And that's actually, if you're interested in it, I would actually definitely suggest you look at that data source.
Thank you.
Yeah.
All right, next is Enze.
Hi, Lin. Thank you for a great talk. I'm just curious, just look at this picture. So it seems that the subsidence only happened on one side of the road. Why it doesn't happen on both sides?
Right, so good question. On this side, what happens is it blocks this road, actually blocks the drainage on this side and this side, and then you just normally those lakes showing here are a white color, so they have surface drainage network that water easily flow across them to each other, but this one just blocked the drainage, the water flow from this particular water body. So the water just accumulate here on this side, and that corresponding to the stronger subsidence on this side of the road instead of the other side.
Okay, thank you. Thank you.
All right, any more questions from the audience? You can unmute your, Kansu.
Hi, yes. Thank you for this great talk. I just have a quick question. What's the application of NMR in like coastal regions or like where there's salty groundwater? Like, is it only detecting, is it like liquid or not liquid, or can we tell if it's salty or, you know, not salty?
Right. Right. A quick answer is the former. It's best surface NMR is best to quantify water content. What's the percentage or in terms of the water content? If you want to use near surface geophysics for quantify, for instance, salinity, the best way to look at is the resistivity. ERT is the best, and it's being widely used. You don't have to resort to the NMR.
Okay. Okay. Thank you.
All right. Do we have more questions from the audience? If not, we'll let you go. I mean, I know it's pretty late in Hong Kong already. Thanks again for a really nice talk.
Thank you very much for having me.
Hope to catch
If
up
you
with
have
you.
any questions, please feel free to contact me. I hope I will be able to see many of you in Austin or a face-to-face setting.
Yeah.
All right, and also
All right.
have happy Chinese New Year to everyone.
Thanks. Happy New Year.
Bye bye.